video, we will discuss the definition of configuration and how it works. And we will discussing the different types of configurations like Cafano plane, Mobis counter configuration, Ray configuration, and Danzer's configurations. Configuration: a set of M points and N lies in a plane is called a configuration. This is the symbol. If each of the M points is incident to the same number C out of N lines, while each of the intersection lines pass through the same number D out of M points. What is the meaning of the symbol? M is for vertices, C is for line, N is for lines, D is for points. What is the meaning of MC? The meaning of MC is how many lines in a particular vertices, like this. This is the example of MC. This is not an actual example, but for our visualization, for further lessons, or for further examples. So like this, one vertices and have a two lines. This is the meaning of MC. Next, what is the meaning of MD? The meaning of MD is how many points in a particular line, like this. This is the example of other visualization. We have one line and 2 points. Note, CM is equal to DN. When we conducting the plane, these are the examples. We have square and rectangle. In the square, we have 4, 2 in MC, 4, 2 in ND. 4, 2 in MC, 4, 2 in ND. So why this is our 4, 2? Because in a plane, we have 4 vertices. In the vertices, we have 2 lines. 1 and 2. 1 and 2. Now we proceed to ND. We have 4 lines. In one line, we have 2 points. Example, one line, we have 2 points. Same as in the rectangle. Now, if MC and ND are equal to each other, now we will proceed to the self-dual configuration. What is the meaning of self-dual configuration? It will configure itself into singularity, like this. 4, 2, 4, 2. Now, she will be a singular configuration like this, because they have the same MC and ND. Now, why if we did not use the self-dual configuration? Just label it 4, 3. 4 vertices. In the vertices, we have 3 lines. 1, 2, 3. We have 6 lines. 1, 2, 3, 4, 5, 6. Have 2 vertices. 1, 2, 1, 2. Same as in the rectangle. Now, if we look at the cylinder, why the self-dual configuration exists? Because in this circle, this is only a line, one particular line, same as in this. Now, let's proceed to the other configuration. The first configuration is a Fano plane. A Fano plane has 7 points and 7 lines that the lines are the side of the triangle. Its altitude and the circle containing all the midpoints of the side. This is the this is the definition of panoplane. How to define a panoplane? First, each pair of distinct points lies on a unique plane. Second, each line contains 3 points. And lastly, the number of points is the same as the number of lines. If we look at this plane, the self-dual configuration exists because MC and ND we will talk about before this is equal to each other. So, how this plane is panoplane? First, each pair of distinct points lies on a unique line. This is the pair of points rather. This is the pair of points and this is a unique line. Second, each line contains 3 points. In this particular line, how many points are there? There are 1, 2, 3. Next, the number of points is the same as the number of lines. So, if we count the number of points or vertices, we have 1, 2, 3, 4, 5, 6, 7. How many lines? 1, 2, 3, 4, 5, 6. And the circle on the center of the triangle is only one line only. So, this is a panoplane. The very unique panoplane exists. So, let's talk about the other configuration. The brief history of Möbius-Cantor configuration. Möbius-Cantor graph, named after to August Ferdinand Möbius, who asked that whether there exists a pair of polygons with p side each, having the property that the vertices of one polygon lies on the line through edges of the polygon and vice versa. And Seligman-Cantor, who found pairs of polygons that, for generalization of the problem in which the points and edges belong to the complex projective plane. So, the Möbius-Cantor graph derives its name from being the Levy graph of Möbius-Cantor configuration. So, this is the brief history of Möbius-Cantor configuration. So, let's talk about the plane. The second configuration is Möbius-Cantor configuration. Möbius-Cantor configuration is a configuration consisting of 8 points and 8 lines, with 3 points on each line and 3 lines through each point. So, why 8 and 3 is the same? Because there an exists of self-dual configuration of 8. So, before we define a Möbius-Cantor configuration, let's talk about the brief history of it. Möbius-Cantor configuration. How to define Möbius-Cantor configuration? First, we have self-dual configuration, same number of vertices in line, and lastly, each line and vertices contain 3 vertices for line and 3 lines for vertices. If you look at this plane, this is a Möbius-Cantor configuration because we have 1, 2, 3, 4, 5, 6, 7, 8 vertices and 1, 2, 3, 4, 5, 6, 7 and 8 lines of it. So, the self-dual configuration exists because MC and ND are equal to each other. So, this is the first example of Möbius-Cantor configuration plane, and this is the other. If you look at this, it's like a biscuits, if you imagine. And this plane have 8 vertices and 8 lines. So 1, 2, 3, 4, 5, 6, 7, 8 and 1, 2, 3, 4, 5, 6, 7, 8. So the self-dual configuration exists in this plane. Have same number of vertices in line, and each line and vertices contain 3 vertices for line and 3 line for vertices. So let's proceed to the other configuration. The third configuration is gray configuration. It has a vertex for every point and every line of the configuration, and an edge for every pair of a point and a line that touch each other. So what is the meaning of this? The meaning of this is for every point, vertex edges has a pair of a vertex edges. So example of pair of vertex edges is this. This is a vertex. This is an edges. So that touch each other. So this is the other pair of his vertex. Touch each other. And like this vertex to this vertex, his pair is this. So like this. The other example is this vertex to this middle of vertex, and this vertex to this middle side vertex. So how to define a gray configuration? How to define gray configuration? Gray configuration has 27 points and 27 lines, meeting 3 lines, 12 points, and 3 points to a line. The example of this is displayed. We have a specific visualization. First is a line with 3 points, and second, the vertex of a point have 3 lines. 1, 2, 3. The second defining the gray configuration is a gray configuration must drawn as a 3-dimensional figure or graph, just like this. And lastly, the gray configuration must have its self-dual configuration. So if there is no self-dual configuration, this must be not a gray configuration. So this plane or a 3D plane is a gray configuration. Have 27 points and 27 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 vertices, and a line with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27 lines. So this is a gray configuration, and let's talk about the last configuration. The last and final configuration is dancer's configuration. Dancer's configuration is characterized combinatorially by having the Kronecker cover over the odd graph ON as its Levi graph. Dancer's configuration is deeply rooted in Pascal hexagrammum mysticum, although the combinational is highly symmetric. So, how does the dancer's configuration exist? Because of conical and hexagonum, the dancer's configuration exists with highly symmetrical plane. So let's look at the examples of Kroneker's graph. So this is the Kroneker's graph, was usually used in science subject like chemistry, biology, like DNA stuff. Next, the Pascal hexagonum mysticum theorem graph. This is the second graph that combine to create a dancer's configuration. So how to define a dancer's plane or dancer's configuration plane or graph? How to define? How to define dancer's configuration plane? So first, dancer's configuration plane have 35 points in line. Second, every vertices have 4 lines and every lines have 4 vertices. So we have an example of a specific visualization that vertices have 4 lines, 1, 2, 3, and 4, and a line with 4 points, line and 1, 2, 3, 4. The third one is dancer's graph plane is symmetrical. And lastly, self-dual configuration exists. If self-dual configuration does not exist in a plane, so the dancer's graph or configuration does not exist. So if we look at this plane, this is the dancer's configuration plane. So let's have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 29, 30, 31, 32, 33, 34, 35 vertices and lines. How many lines? 35 lines, and I don't want to count it because so confusing to count this, very disgusting, because this is my draw and this is for the video. This is the end of the video of defining the configuration and discussing the other configuration. So thank you for watching and listening to my video, and this video is my project to modern geometry by Professor Tan.